Okay, class, we're still in respiratory, but we're going to a new PowerPoint called acid-base balance. Now, this one can stand alone, actually, because acid-base balance involves several areas, but I'm putting it in the respiratory, but of course you can retrieve it separately, and you can even look at the videos because they'll be labeled acid-base balance, so you don't have to do that completely. Okay, anyway, let's get started. All right, so we're just going to walk through. I think it's like 30 slides on what I have. All right, first of all, I'm going to say that an acid, according to Lowry-Bronsted, now there are different definitions for an acid, but we say an acid is a proton donor. Now, it's symbolized by H+. Okay, why? Because hydrogen has an atomic number of 1, which is the proton number, and an atomic mass of 1, which means it has no neutrons. Now, off the chart is neutral. That means it has 1 electron. So if it loses that 1 electron, what is it? A raw proton. That's why it's symbolized by H+. So an acid is a proton donor. A base is a proton acceptor. And a buffer, we'll talk about briefly, is a chemical that can resist a change in pH. It tries to hold your pH in the proper range. Okay, so let's go further. The normal pH of your body fluids is this. The pH of the blood is about a 7.35 to 7.45. That's what you want to hold the blood pH in. The blood pH. About a 7.35 to 7.45. I'm not ready for this over here, but if you look over here, you can kind of see, I'm going to take it up a little bit, a little notch. You can kind of see this person, this Jane Doe, is in normal, pretty much in normal range or close to with the pH. Okay, in this particular, just a little bit outside. What's that? 7.46. Okay. But normal is this. Now, that person is a little bit acidic, a little bit basic right here, because this is an arterial blood gas. The only time it's mandatory to draw blood from an artery is to do an arterial blood gas, because we're not interested in venous blood. So arterial blood is about a 7.4. Now, why? That's right in the middle. And venous blood about a 3. Venous blood is a little more acidic. Why? There's more CO2. Remember, CO2 mixes with water. Inside the cell is 7. Now, if you keep the blood right, then everything else will be right. Okay? So that's kind of your values. Okay. So over here, since this is arterial blood gas right there, that's a little bit high there. So this person is a little bit alkalotic. And we'll talk on that. Okay, it's just a generic deal here. All right. And here's there's the measured values, but here are the temperature corrected values for what they are. So see that this is 7.43, which puts them in range on the corrected value. It puts them in the range, but still a little bit above the 7.4. Anyway, let's go a little further. Alkalosis or alkalemia. Arterial pH rises above 7.45. Acidosis below 7.35. Physiological acidosis. Okay. pH buffer. What's a buffer? Now, buffer that resists a change in pH. It's a substance that tries to do that. What is a buffer? Okay, now you can get if you go back to I know you're in ANP 2, but if you look at my ANP 1 PowerPoint slides in chemistry or inorganic, look at pH, and that'll kind of give you a better idea, because I'm just hitting high points here, assuming you already know. All right, but let's go here. pH buffer. What it is a weak acid in equilibrium with its conjugate base. A weak acid in equilibrium with its conjugate base. Now, a weak acid does not completely dissociate. See, an acid has to dissociate, liberate an H+. A strong acid completely does. So if you go to my chemistry section, you can see what I'm talking about. Okay. Add outside acid to buffer. It combines with the base to make more weak acid. So let me show you what I mean. First of all, what is a buffer? A pH buffer resists the change in pH. A pH buffer is chemically composed of a weak acid and its conjugate base. All right. Now, this is a generic. A is a placeholder like X in math. It's an anion because H is a positive, anions a negative. Now look at this. All of these have the proton thing. Okay. But are all of these substances acids? And the answer is no. Let's go to the next one. The answer is no. Because even though this has protons, it doesn't liberate any. It doesn't liberate any. Now, these do. But this only liberates one, and you liberate two, let's say. So this is a weak, it's an acid. This is an intermediate acid. And this is a very strong acid. Why? Because it donated all of its protons. So therefore, to be a buffer, I need either this one or this one. I need a weak acid in equilibrium with its conjugate base. Now, what's the rationale on that? The rationale is, if this is in there, then no matter if you insult, and an insult basically in clinical is anything deviates you from homeostatic range. No matter if you insult it with base, it combines with acid. Now you say, what do you mean by an insult? I'm going to come over here. So let's say that you drink root beer, okay, or you eat some baking soda or milk of magnesia, various things of this nature here, pickles, that would insult it. Now, also internal chemical reactions. See, in your body, you're doing chemical. You don't have to bring it from the outside. That's insults, and that would drive the pH out of range. So if it's insulted with acid, it mixes with the base. Because see, that's a base. That wants, and if it's insulted with acid, with base, it does this. So whatever you have is this. The only time that the buffer is going to fail is when the concentration of the insult exceeds the concentration of the buffer, which means you don't have enough buffer units for the insult units, to say it another way. Okay, now again, go back and kind of tie this into my ANP1. All right, so a buffer resists a change in pH. Let's just say it like that. All right, we come here. So what buffers do you have in your body? What buffers do you have in your body? Well, you have the bicarbonate buffer system. That's the main extra. That's the one we were talking about. Remember when I said CO2 being carried as a waste could still be useful as forming a buffer. That's the bicarbonate. The two non-bicarbonate are the phosphate buffer, which is a breakdown of phosphoric acid, just like you did the carbonic acid, and proteins. See, proteins are good as buffers because some amino acids are acidic and some are basic. So they can soak, so acidic amino acid can soak up a base, and a basic amino acid can soak up an acid, okay? Now, all of these buffers are communicating with one another. That means all of them are working together. That's why they call it the isohydric principle. They're working in a confluent manner. So they're not working independently. They're all helping each other out. All right? They're all helping each other out. Now here's comes from a book, a medical book, to kind of show you, it's hard to see. If this is 100%, you're showing it kind of in a percentage as to who contributes so much to everything. Okay. So right here, you can see that's the plasma bicarbonate, and you can glance at it, but this is just to give you a relative idea. I'm not going to question it, a relative idea of how all of these different buffers are contributing to the whole aspect of buffering in the body. Okay. All right, we'll go a little further. Okay. Now, when we go further, bring this in a little bit here. See, a clinical insult is anything that attempts to drive the body out of homeostatic range. So always keep that in mind. All right. So here we are with this here, and I'm going to put it over here. Okay. Now here, remember I told you the only time it's mandatory to draw blood from an artery is to do an arterial blood gas. Here's kind of these are the main things we're going to look at when we go through this, is the pH that you get, the pH, the PCO2, which is really the P little a CO2, and the P little AO2, arterial CO2 and arterial O2. Okay. Now these are the only things I'm really interested in, is this and this here in this particular aspect there. There are other things, base excess, all kind of stuff. O2 saturation, all this stuff like this. But for us, we're just interested in these here with this. If you go into a respiratory program, they'll go through all this other stuff. All right. So that's the normal. We want to keep the pH between a 7.35 and a what? 7.45. A 7.35 and a 7.45. Okay. Now, why am I putting, well, let's look at the logistics of my course. Why am I putting acid base within the lung chapter? And then why am I rearranging the textbook to next go to kidney? See? Why am I doing that? Because the two main organs that control your pH in your body, the two main, are the lungs and the kidneys. So what three things deal with your pH in the body primarily? Actions of lungs, we'll see. Actions of kidney and the buffers. Actions of lung, action of kidney, and the buffer. Those three things. So now you can see why this chapter is going to come after this chapter, even though that's not true in the textbook. Because remember, I'm rearranging the textbook to make it more clinical. So here, we want this to be at a 7.35 to 7.45. And there are three players trying to do that. Lungs, kidneys, and your buffers. Okay? All right. So now we go, so that's the normal. Now we start getting into clinical signs of when you get out of range. Okay, so I'm going to close this one. So we've done now acid base A, we'll say. Acid base recording A.